Hello, good afternoon, everyone. My name is Reyes Mani, and I work for the company Allied Scientific Pro. So, the title of today's webinar is Photometry and the Lighting Passport Instrument. Welcome to this webinar. I've given this webinar a number of times, and every time I try to include some new material that reflects the work of the company, and also it won't be repetitive for uh, attendees who attended for more than one time. So the webinar will be recorded, and the recording will be sent to you within a few days. And my email is also here. If you have any questions, you can send me. Uh, so mostly the photometry material that is in this webinar is related to the parameters that the lighting passport instrument could measure. So they are closely correlated to each other. So these are the this is the outline of my talk. There's a long list, so I try to do as much as I can. I'll give a little bit of basics about electromagnetic spectrum, the eye response function, talk about photometry, radiometry, solid angle, uh, understand more the units of photometry, difference between photometric and radiometric units. Then I'll go into describing instruments that could measure photometric quantities. And I will touch on the UV also, although it's not really part of the photometry. But I thought I mentioned a UV instrument here because of its usage these days for disinfection purposes. And we'll talk about the photosynthetic photon flux density, PPFD, blackbody radiation, color temperature, and these are all important for understanding the TM30 report, which I'll get to later. So all of these parameters will be there. So I'll show the 1931, 1976 chromaticity diagrams, the UV, CRI Index, and then I'll get into the TM30-20 report. Earlier versions were TM30-15 and 18, and I'll talk about the Annex E also of the TM30. Uh, then I will show you how to generate the TM30 report using the Excel calculator. There will be a web calculator coming soon, but it's still not there. So when it becomes available, I can share the link with you. And then the SSI parameters that is used in the film industry. And finally, I'll talk about replacing high-lux model with the standard Pro with the ND filter attachment. So this is the list. Okay, so this is the electromagnetic spectrum. I'm sure everyone is familiar with this. All the way from the gamma rays on the left to the radio waves on the right, goes through X-rays, UV, visible, infrared, microwaves, and from left to right, you can see that the wavelength is increasing all the way from a few nanometers to 1 kilometer, and then the frequency is uh, from left to right is decreasing. And the visible portion of the spectrum is a small section here, surrounded by the infrared to an ultraviolet on either side. And I define it as the 400 to 700 nanometer range. So you can also see I've shown the 700 to 780 nanometer, which we call far red. And then the 380 to 400 is part of the UVA spectrum, and that is the range of the lighting passport from 380 to 780. So it measures a little bit of UVA, all of visible, and all of far red. Okay, so let's talk about eye response function. So the response function has this Gaussian profile with a 555 nanometer peak, and which is this kind of green. And the question is, why is it at 555 and at not any other wavelength? Is this a coincidence? So the answer is, uh, we basically evolved under the sun. The sun is a black body radiation, is a black body radiator, and it has a peak at 555 nanometers. So our eyes adapted to this wavelength as the peak sensitivity. So it's not a coincidence. Now let's look at the difference between the radiometry and photometry. So radiometry is more general. It could measure light in any portion of the electromagnetic spectrum, right from the infrared to visible to UV, and more, mostly focusing on infrared, visible, and UV. And it has units such as watts for radiant flux power, irradiance, watts per meter square, radiant intensity, watts per steradian, and etc. These are all radiometric units. However, photometry only focuses on the portion of the spectrum which is in the visible light, which also includes that little bit of UVA and far red. So 380 to 780 nanometer. So uh, it's the science of measuring visible light in the units that are weighted according to the sensitivity of the human eye. So the response function modifies the measurement, and therefore it's only valid where there's a value for the response function in the visible spectral range. So you have units such as lumen, luminous flux power, lux, which is illuminance, candela, luminous intensity, etc. These are all photometric units. So outside of this region, 380 to 780, photometric units do not make sense, or measurements do not make sense. It has to be within this range. Now, in order to understand photometry a little bit better, we look at this concept of solid angle. This is again basics. So imagine you have this cone with its apex at the center of this sphere, and it's intersecting the surface of this sphere with area A. So if you divide the area A by square of the radius, that will give you the representation of this three-dimensional angle, which we call solid angle, and its unit is to radians. So because a sphere has a 4 pi r square surface area, if you divide that full surface area by r square, the maximum possible solid angle that a sphere could provide is 4 pi. Now here, again, looking at some of the photometric units. First of all, we look at the luminous intensity that has a unit of candela. And this candela actually comes from candle. So it used to be a plumber's candle, and they used it for melting solder, lead solder, when they were joining water pipes. And if you look at the intensity of this candle, it's roughly 1 candela. So from the 1 candela, we can define lumen. So imagine you have a source of 1 candela at the center of a sphere that has a unit of one, that has a radius of 1 meter. And this cone uh, also intersects the surface at the 1 meter square, uh, basically intersection surface. So the solid angle would be 1 meter square divided by 1 square, which is 1 steradian. So this is a 1 steradian solid angle, and this is a 1 candela light source. The amount of light that goes through this surface would then be 1 lumen. Okay, so lumen per steradian will give you candela. But because this lamp is emitting in all directions and there's 4 pi solid angle, if you measure, if you want to know what's the total luminous flux of this lamp, it will be 4 pi lumen. Here's again comparing radiometric and photometric units. So you can see this is a candle that is shining this basically luminous flux. It has a radiant luminous intensity in candelas, and this falls on the surface on a certain area. So the amount of lumen per meter square would give you the illuminance, which is called lux. And if you look at it with your eye at an angle, then there's this cone that is defined here. If you divide the lux per steradian, that will give you basically luminance. So luminance is lumens per meter square per steradian, or you can call it candelas per meter square. The corresponding radiometric units are radiant flux in watts, radiant intensity in watts per steradian, uh, irradiance in watts per meter square, and radiance in watts per meter square per steradian. So now the question is, which photometric quantities can be measured by which instrument? So if you want to measure photometric quantity, you may have to make sure you're purchasing the right instrument. So from left to right, you look at the lighting passport. This could measure the photometric unit of illuminance. Uh, I should also mention that it could also measure the spectral PPFD, the photosynthetic photon flux density, micromoles in micromoles per meter square per second per nanometer. This is a radiometric quantity, but I wanted to mention this because the other photometer cannot measure this. So as far as the photometric units are concerned, it could measure lux. And you can also buy photometer, for example, a light or photometer that give you the total illuminance in lux, but it doesn't give you any spectral information like lighting passport. Or if you want to measure the luminous intensity, you need to have a goniometer where the detector is going around the circle around the source and measures at each solid angle, and this will give you the candela. And once you integrate all the measurements, you get the total luminous flux in lumen. And for measuring total luminous flux, you can, or in lumen, you can also measure it with the integrating sphere, where you install the source in one port and the detector would be in another port, and the reflecting surface of the integrating sphere will basically direct all the reflected light towards the detector, and you can measure the lumen. So let's talk a little bit about UV, which is right next to the uh, visible. So the UV is divided into four portions. The UVA from 315 to 400, uh, UVB 280 to 315, UVC from 200 to 280 nanometer. And below that, down to 10 nanometer, it's the vacuum ultraviolet, because the radiation is basically absorbed by air. So in order to see it, you have to create a vacuum. So UVC is very popular these days because of the coronavirus situation. It can be used for uh, disinfecting surfaces in hospitals and buses. And we have this instrument called SRI 2000 UV illuminance meter. It has a range from 250 to 850 nanometer, which could measure that. And here I am showing you 266 nanometer quadrupole neodymium YAG laser scattered emission, which I measured with the SRI 2000. So you can get the readings in watts per meter square. It's a radiometric unit. This is the irradiance, and if you multiply by time, you can get the dosage that is required, that it gives you, and use that for disinfection. So you have to make sure that you're properly protecting your eyes and skin, because UVC could be harmful. So you need to have like a glass shield on your eyes and cover all your skin. We also have a new unit, SRI 4000, that has a range from 200 to 430 nanometer. And this 2000 is a 10 nanometer resolution spectrometer, whereas the 4000 is a half a nanometer, but it has a smaller range from 200 to 430 nanometers. So let's talk about the particle nature of light to understand the PPFD. So the wave nature of light was known since uh, 18th century, and all kinds of experiments like diffraction, interference, uh, etc. Were performed to show that light has a wave property. It also has particle property, as was shown by many scientists at the beginning of the 20th century. And this is the Planck's formula. I'm sure many of you are familiar with it. E equal to h nu, or hc over lambda. So it shows that as the wavelength increases, the energy of the photon decreases, and as the wavelength decreases, the energy increases. So the light is emitted in the form of photons. And this is very useful in horticulture because in horticulture, the plants and the photosynthesis process don't care about how much watts per meter square is falling on them. They rather care about the number of photons. So in order to convert the irradiance into number of photons, we use this E equal to nh nu, where n is the a number of photons. H is the Planck's constant and nu is the frequency. So you can convert that. And then we use this unit called micromole. So mole is a unit that is borrowed from chemistry, 6.023 into 10 to the 23, which is the Avogadro's number. And a micromole is 1 millionth of that, which is 6.023 into 10 to the 17. So rather than saying we have 6.023 into 10 to the 18 photons per meter square per second, for example, we can just say you have 10 micromoles per meter square per second. And this is much faster and easier to use. Now, if you look at the spectrum, we have this software called ESCAL, this app called ESCAL, which is designed for horticultural purposes. And if you look at the radiant intensity versus wavelength, you can see in this case that blue is higher than red. But if you convert this into PPFD units, you can see the red came up and the blue went down. And that's because the red photons have less energy than the blue photons. So in order to make up, for example, for a, for 1 watts per meter square, you need more of the red photon than blue photons. So this will give a higher weight to the red than the blue. So when you convert to PPFD, the curve uh, value would go up on the red side and go down on the blue side. Okay, so let's go to black body radiation. Black body is a perfect absorber and a perfect emitter of light, and it has this typical curve. It's a continuous curve that has a maximum, and so both sun and the earth could be approximated as being the black body. So the sun has about 5,800 Kelvin, and its peak is at around 550 nanometers or 0.55 micron. And the Earth is a lower temperature black body as 300 Kelvin, and the peak is at around 10 micron. So it's a rule for black body that as the temperature increases, the peak emission moves towards the shorter wavelength. And this is what we can see here. Now, from this, we go to color temperature. So when you heat a body, for example, a metal pot, like you can see here, the temperature, as the temperature is rising, you can see there are color changes in the metal. So first it's red color, then it turns yellow, then it turns white, and then it turns blue. So you can associate these colors to a particular temperature, and that's why we call it a color temperature. So it's measured in Kelvin, and you can also see the same thing in this position of the sun in the sky. So during early morning at dawn, you can see there are smaller color temperatures, 2400, 2700, and then at noontime as the sun rises, the color temperature increases to 6500. So for higher color temperatures, we call them cool colors, and for lower color temperatures, we call them warm colors. There is counterintuitive. So if you want to get warm colors, you need around 2700 to 3000, and for cool colors, about 6500. And we also have a correlated color temperature. So a body could show a color temperature of 3000 Kelvin, but his actual temperature is not 3000 Kelvin. His color temperature is 3000. So you can get an LED that has a certain color, a white LED, and say this is a 3000 or 6000 Kelvin color temperature. Uh, so that's how you define the color temperature. Uh, so we also have to understand the chromaticity diagram. Again, all of these are provided by the lighting passport. So it maps the human color perception in terms of two coordinates, x and y. So you can see this curve that looks like a loaf of bread, and the surrounding is all monochromatic. It's called the spectrum locus. So different wavelengths are around here, and a source of light that is a mixture of colors could fall anywhere in between here. So it has a coordinate x and y. You can define its chromaticity in terms of x and y. This is actually a 1931 diagram by CIE. You also have a 1976 version. Uh, so how to calculate the chromaticity coordinates and find the correlated color temperature. So I just don't want to go into too much math, just very briefly, just to understand how these numbers are provided. So you take the spectral power distribution, multiply it by the reflectance curve. If you are measuring reflectance, if you're directly looking at the light, you don't have to take into account the reflectance curve. And then multiply by the color matching functions, which define the sensitivity of cones in your eyes, and then you can integrate this product, and that will give you capital X, capital Y, capital Z, which are the tri-stimulus values. And then from there you can calculate the 1931 chromaticity coordinates X and Y from this formula. Z is just 1 minus X plus Y, so you don't really need to calculate it. Then you have to do a transformation to the 1960 color coordinates, whose units are U and V. So using X and Y, you can calculate U and V, and then you would see once you calculated U and V, it will fall on a point in this diagram. And there are actually some isothermal lines here that are perpendicular to this black body curve, which is shown here. So wherever that point falls on any of these lines, that will be the correlated color temperature of the body. But it has to be done in the 1960 version. So you also have the 1976 chromaticity diagram, which has a more uniform color spacing. And these are the ISO-CCT lines that are shown in the 1976. So the, the, the source could fall below or above these lines. But as long as it falls on one of the lines, then you can define the correlated color temperature. What about the DUV? What is DUV? This is another parameter that Lighting Passport provides. So DUV is a measure of uh, is a measure that is required for whiteness of the light source. So depending on whether it's above black body curve or below the black body curve, you can say it's a positive or negative. So when it's negative, it's the light source is more reddish. When it's positive, the light source is more greenish. So it's important to know, uh, is it above the black body or below the black body? And that's a measure, both CCT and DUV are a measure of whiteness of a light source. So this DUV is calculated from the 1960 UV diagram. You can also calculate it from the 1976 because there's a scaling factor that is there. The two-third of V prime is equal to basically V. But we are not getting into the details of that, just to understand what DUV is, how it is calculated. It's like a black box, so that the value is given to you. Then we go to CRI index. So basically, CRI index will show you how effectively a light source could bring out the true color of an object. So if you hold a red apple in the sunshine, you can see its true red color. But if you hold the same apple under, say, some kind of fluorescent lamp or some kind of sodium, high pressure sodium lamp, you won't see its true color. So although the color temperature is the same for all of these, the CRI values are different. So you can see here 97, good color, and as you go to lower CRIs, it has deteriorated its color. So CRI would define the CRI index would define how original the color would be under that light source. And the higher the value, the more original it would be. So I very briefly want to mention how CRI is calculated in the CIE's standards. Not going into too much math, just very, very briefly. So first of all, you find the chromaticity coordinates of the light source in 1931, which we already covered. How we do that, which is on this top right corner. And then after that you uh, do the transformation to 1960 and find the CCT of the source. Okay, so correlated color temperature. Once you find the CCT, you can choose a reference source based on the temperature of the CCT. If it is below 5,000, use a black body source. If it was above, you use a CIE standard illuminant D. And then you have these 8 color samples, R1 to 8, R8. You illuminate these 8 color samples with the reference source and with your test source. In fact, there is no real uh, illumination. They just multiply the reflectance function of these by the spectrum that you measure from the test source and also the reference source. Then you would find the chromaticity coordinates of light for each sample for the test source and the reference source. Then you have to do another transformation to the 1964 version of CIE, which has these coordinates U star, V star, and W star, and you would find the Euclidean distances of between each pair of points. So the test source and the reference source would not have the same chromaticity exactly. If you find the distance for each color, that's a Euclidean distance, which you can calculate. Once you calculate uh, this Euclidean distance, you can find R1 to R8 by using this formula, 100 minus 4.6 into delta EI. And then when you average it, that will give you the RA, which is your CRI index. We have also extended this to 7 by 7 saturated colors because these 8 were not enough. So we have now R1 to R15, which includes R9, the red color, which is quite important for the lighting industry. So if you do the same procedure and average R1 to R15, you will get the RE. So both RA and RE are provided by Lighting Passport. These are basically the shifts that I was talking about at the reference source and the test source. The chromaticities don't fall on the same point, so you could measure the uh, Euclidean distances. And this has to be done in the 1964 diagram. I've shown it here in the 1960, but for the calculation, it should be done in 1964 uh, color space. So here are some examples of CRI for different light sources. So tungsten lamp, it's a black body source, has a very good CRI of 100. And then you can see fluorescent lamp, 50 to 99, tungsten halogen 95, compact fluorescence 82. And this only makes sense for polychromatic light for low pressure sodium because it's monochromatic. It has only two lines. It doesn't make sense. But high pressure sodium 25 and white LED 70. So this represents how original the color of an object would be under these light sources. Then we go to dominant wavelength. So if you do the chromaticity measurements in 1931 and you get a sample point, your reference would be somewhere in the center because it's a black body. So it would somewhere fall in the center here. So if you join the reference source to the test source and extend it so that it hits the boundary, or which we call the locus points. Sorry. So we showed this at some point. Yes, the spectrum locus is the boundary. So when you hit that boundary, then you have reached a particular wavelength, which we call the dominant wavelength. So it represents the closest monochromatic light that resembles the polychromatic source of light, which is under test. So if you're here around 560, 570, then you know this is your basically closest monochromatic light that resembles your full your polychromatic light. Now we go to the IES TM-30-20, which is an ANSI IES standard. And trying to understand why this new standard was created, why we couldn't continue with the CIE's standard. So you can see three pictures here. This is the original, this is a desaturated, and this is a saturated picture. And according to CIE, both of these, they have RA of 70. This is a CRI index. So the CRI index is just an average value which shows a measure of fidelity. It doesn't talk about saturation or desaturation. So, according to CIE, these two are the same. There's no difference between the two. Whereas, as far as the chroma is concerned, they're widely different. This is desaturated and this is saturated. Also, CRI has limited test color samples that the do not reflect the real world of today, which is more complex. So, for this reason, the Illumination Engineering Society, IES, has created this TM30 standard. The earlier versions were 15 and 18. This one has 99 color samples. And instead of having just one index, RA, it uses two indices, RF and RG. So RF is the fidelity index, which is very close to the CIE's RA on a scale of 1 to 100. And RG is the gamut index. It deals with chroma and hue shifts. Its value normally changes between 60 to 140. So for RG values, which are over 100, it shows saturation, and below 100 shows desaturation. TM30 also has better graphical representations that CIE's standard doesn't have. So you can look at the graphical representation and immediately understand the performance of the light source. So how to calculate RF and RG in TM30? And very briefly, I want to just quickly go through different steps just to understand how these numbers are provided. So first of all, you get the 1930 one chromaticity coordinates. Then you would basically transform uh, into the 1960 and get your color correlated color temperature. Uh, then after that, depending on the value of CCT that you get, you would uh, you would you would decide what reference source you need to choose. Uh, Below 4,000 is a black body. Between 4,000 to 5,000 is a blend of black body and CIE daylight, and above 5,000 is CIE daylight. Then you would illuminate these 99 test color samples to get their chromaticity, and you have to also do a transformation to this new color coordinates CAM02-UCS, which has A prime and B prime as its variables and could be positive or negative in both axes. So you could see that you get a bunch of red dots, which represents the test source, and a bunch of black dots, which represents the reference source. Then you have to calculate your Euclidean distances using this formula. It's actually done in 3 dimensions. You're only looking at A prime and B prime, but there's also a third dimension, J prime, here that we are not showing. So you calculate these Euclidean distances, and then you can average them out, the 99 values, and then use this formula to get R dash F, 100 minus 6.73 into this average. And in order not to have a negative value, you do a log transformation and you would come up with RF value. So this is how you get the RF value. To calculate the RG values, you would divide this coordinate system into 16 slices, something like pizza slices, you can say. So from 1 to 16, and then you would average out all the black dots and all the red dots in each slice, and that would give you a polygon like that, a black polygon and a red polygon. So in order to calculate RG, you would measure the area of the red polygon divided by the black polygon and multiply by 100. So this could be either, the red area could be either more or less. So that's why your number could be more or less than 100. You can also normalize the reference source, so you get a full circle, and then your red polygon becomes a distorted circle, or it could be looks like an ellipse sometimes. So you can see here, wherever you have the red inside the black, it shows desaturation, and outside the black, it shows saturation. There are also some arrows tangent to the circle, which represents hue shifts. So the TM30 deals with both chroma and hue shifts. Here is a RGRF graphics. So all the practical light sources are within the white triangle. So the dashed triangle do not represent any practical sources. In this case, you have uh, a complete black body. So your both black and red circles, they coincide, and you have a 100 coordinates. But you can also have something like this, where you clearly have saturation. So the area of saturation is more than the area of desaturation. So on average, it's a saturated light source. And that's why you could see its RG is 115 and RF is 65. And mind you, you can have our RG of 115 and our F of 100. So once one of the values changes from 100, the other will also change. So you can not have one of the values being 100 and the other a different value. It's either 100 or two different values. So here I show a desaturated light source. You clearly see that it's a deflated ball, and this desaturation area is higher or larger than the saturated area, and its values are 65 and 85. RF 65, RG 85. Okay, so now after going through all of this, we are in a position to look at the TM30-20 color rendition report. And let's try to understand this. And after that, I will show you how you can generate this report. So here you have the color vector graphics, your black test source, your black reference source, and red test source. So you can see in bin 1 there is desaturation, in bin 5 and 6 there is saturation. So you have your RF values, RG here, and then here RCS H1. So CS stands for chroma shift in bin 1. Because red is quite important for lighting industry, they mentioned this RCS H1, which is minus 10%. So uh, here you have RF H1 for the bin 1 is 83. So these four parameters are here. And then you would also have your CCT and DUV values mentioned here. And then you have these Annex E parameters, P, V, F, preference, vividness, and fidelity, which I will get to later when I explain what Annex E is. Here you have two graphs here, bar graphs. They show the chroma shift in each of the 16 bins. So here you can see minus 10% for bin 1, which is the same as here, and then so on. In some areas, you can see 5 and 6, there is saturation, and you can see them here as well, and so on. These are the chroma shifts that you can see. So if the arrow is counterclockwise, is positive, it is sorry, is clockwise is positive and is counterclockwise is negative. Uh, so for example, 4 is is counterclockwise. So actually, I said it reverse. 4 is counterclockwise, so it's counterclockwise is positive and clockwise is negative. So these are the hue shifts. And then you also have the fidelity for each of the 16 bins. And you can notice that none of these values are negative. They're all positive because of that log transformation that I talked about. Here you have your black body source, reference source. This is clearly a fluorescent lamp. This is the test source. And down here you have 99 RF values for each of the 99 color samples. So that summarizes the TM30 report. Here again, another values are shown here. This is more like a black body, so 96, 102, closer to 100. And now let's talk about Annex Z so we can understand the PVF parameters better. So this Annex Z provides some guidance to apply the measures of TM30, and it describes important considerations for specifying light source color rendition. And you're going to have some subjective qualities such as naturalness, vividness, preference, etc. included in there. These are recommended criteria for 3 design intents and 3 priority levels. And they're applicable in the interior light levels of 200 to 700 lux. So you have color preference, color vividness, and color fidelity. These are the 3 possible uh, design intents, and they have priority levels 1, 2, and 3. So what each one of them mean? The preference design criteria wants to create a pleasing, natural looking environment. Uh, the vividness wants to focus on the how the scene appears vibrant, like for example in an amusement park, but doesn't really care about the pleasantness of it. And fidelity focuses on achieving similar color appearance relative to the spectrum of the reference light. And you can see that each criteria has its own uh, basically rules. So so you could have high values for two of them and low value for one of them. So low value for one would accommodate having higher values for the other two. So if we go back again, you can see in this case we have P3. Let's start with this P1 V3 F1. So you can say it's very pleasing, it's so vivid, and it has a very good fidelity, which you can also see from the curve. And in this case, P3 has so pleasantness, and V minus means F minus means it doesn't satisfy any of the criteria for vividness or fidelity. And so, for example, here, if your light source, if the RG is less than 100, it doesn't satisfy vividness, so it'll be a V minus. Or in this case, if your RF is less than 85, it doesn't satisfy fidelity, so it'll be a F minus. So that's how we get these PV parameters that are on the top right corner. So what about the lighting passport? We have already upgraded it to TM30-20 report. So you can see all of these parameters, RF, RG are there. The color vector graphics are there with the arrows. So we provide this test source, reference source. We also have the RF, RG versus RF curve that I showed. And this is the point that is shown in here. And we also provide the 1931 and 1976 diagrams, chromaticity diagrams. So now I want to show you how you can generate the TM30 report using the lighting passport data, and I'll give you a demo of how you can do that. So how to do that, I'm sure some of you have been using SGM Plus, which records the data in the cloud or on the cloud. And once you go on your spectrumgenius.com on your profile where you have your data, you can just use this download to download the CSV Excel file that has all the data. And for those of you who are using the PC software, you can again use this download button here. Of course, you have to first specify uh, under settings which directory you want this to be saved as, and you can retrieve your data from there. So in order to generate the TM30 report, the first step would be, so first step would be actually to export the data from SGM Plus or SGPC uh, on your desktop. And then you would need the TM30-20 advanced calculation tool. It's a free Excel calculator that you can get at the following link. So I will send you this link over the chat. You can go there and it asks you a few information, and you can download that. So I'll send you this. So you can go ahead and download that from that site. If you have any problems, let me know. It should be very easy to download to find that Excel calculator. And now, after you do that, you open the Excel calculator and go to the calculator tab. So let me do that. I've already opened the Excel calculator. So here is the Excel calculator. Okay, so this is the calculator tab. And then I also have some files which I have downloaded from the SGM Plus. So in this case, you can see this is a fluorescent. So I want to calculate for a LED. So I'll go there to the LED, and then I would copy all this irradiance data. So I'll just copy it. So I'll say Control C, and then I come to the calculator, and over here I put under SPD the first row of SPD and say Control V. So once you do that, you can click Compute. Compute. Let me bring it over here. So see what happens to the spectral curve here once I click Compute. So it changed to an LED spectrum, and all these curves also changed. So it computed the report for the LED spectrum, and in order to get it, you can go to the full report, and here is all the values for the LED, and then you can go here, File, and you can export that into a PDF. Okay, so you can create a PDF file out of this, or you could use save as or print as a PDF. PDF file. Yes. So convert to PDF. So this way you can go ahead and create your report. So let me show you another demonstration. For example, I want to change it back to fluorescent. So now I'm going to go to the fluorescent file. I copy the fluorescent data, SPD of the fluorescent data, Control C, and I would copy it here under SPD, Control V, and then pay attention to the curve. See what happens when I click Compute. It goes back to fluorescent, and all these curves change. Once again, you go to the full report, and basically you can print out this report. All right, so that was that. And next we would go, so I demoed this. There is also the uh, web calculator that is coming up soon. Uh, so that would look like something like this. It's not ready yet, but it looks like something like that. And then you just hit create table. You basically click create table, and then you would paste your spectral data here in the column that is created, and then you would just say calculate, and that will give you the report, and you can print your report. Next is spectral similarity index, SSI parameter. So this has high demand in the filming industry because the film stocks, they were all designed to work with the daylight and tungsten lamp, basically black body sources. And because the new technology is based on LED, this is creating some problems, undesirable color rendering issues. So in order to compare and quantify the difference of the light sources to basically uh, the difference of the light sources to these black body sources, this SSI parameter has been created, has been introduced by Academy of Arts and Motion Pictures. So you need to specify a reference source. The scale is from 1 to 100. So here you can see there's a LED spectrum, and this is the black body spectrum. So it would basically measure the average variance of the light source with respect to the black body source, and it will give you a number from 1 to 100, and the closer to 100 it is, the closer the source is to the black body source. So numbers close to 100 means good SSI and close to black body. This has already been added to the lighting passport. uh, these existing color metrics would not work for this because they're all based on human eyes, but for the photography, they use digital cameras. So here is a measurement that I took from a fluorescent lamp using a lighting passport, and you can see the curve that shows the SSI parameter. and it also gives the SSI parameter as 36%. Finally, the last topic, I'll talk about replacing the high lux unit with the standard Pro, the ND filter. As some of you may know, we have discontinued our standard high lux model that used to measure from 20 to 200,000 lux. So our standard Pro measures only from 5 to 50,000 lux. And the question was how the customers who are interested in higher power lamps could measure from 50 to 200,000 lux. How to do that? Because we don't have this high lux unit anymore. So we decided to do some testing with some neutral density filter. There's this OD point 0.6 from Newport that we got, and some kind of holder was designed for it that fits right on top of the last lighting passport. And we got a hold of two high power lamps, one at 5000K and one at 3000K, and did measurements with and without the filter. So the transmission of the filter was measured to be about 23 to 24%. This is using the Lighting Passport transmission app, and it's pretty consistent, pretty constant along the spectrum 380. And then we illuminated, we measured the spectrum with and without the filter. And what we found is that the TM30 values are not affected. So here, filter, this is a 3000 lamp, 3000 Kelvin. Filter, no filter, we have similar TM30 values, 85, 85, 94, 94. And for 5000, we have 86, 86 RF and 895, 96 RG. So the TM30 values are not changed by the presence of the filter. What is affected is the color temperature that basically is higher by 7% for the filter case as compared to no filter case. So you can see 3105 and 2944. Similarly for this one, 4686. This is no filter, filter 5000. So the conclusion of the test was you can use the OD point 0.6, the neutral density filter, to measure luminances between 50 to 200,000 lux, 50,000 to 200,000 lux. And the multiplying factor of 4.17 should be used to calculate the illuminance after the measurement. TM30 values remain the same, and the color temperature increases by 7% when the filter is used. So we have introduced a software feature that automatically does the adjustments for you. So once you put this under neutral density filter on, then it will just do all the calculations. So automatically multiplies by 4.17 and corrects the color temperature, and you're good to go. So that brings us to the end of our webinar today. I want to thank everyone for attending and listening to this. We also will send you a feedback form if you have any suggestions to improve the webinar, anything that you wanted to be included, or any criticism, anything you could put down in the webinar feedback. I'll be glad to read it. And at this point, I will just would like to uh, ask anyone who has any questions. You may, uh, yes. So you may be able to. If you have any questions, please feel free to ask. Here is a question. You may have said so, but what ND filter are you referring to? ND and ND filter are not always clean, depending on manufacturing thickness of the ND being. Well, it's a neutral density filter from Newport, which is a really reliable company, and it has a constant transmission of 23%. Any other question? Anyone else has any question? free to unmute yourself and ask anything. This is my email also if you have any questions. Sorry, I made a typo in here. So if you have any questions, feel free to ask. So Armani at allied-scientific-pro.com is my email. All right. I guess there's no more question. If there's anything you could think of, you could email me and I will be glad to discuss with you. So I want to thank all of you for attending this webinar one more time. And okay, I will have questions, but right now I'm overfilled with info that I will have to digest. I will store your email address. Okay, yeah, definitely, Thomas. We will send you the recording in a few days, and feel free to watch it a second time, and send me a list of your questions, and I will be glad to answer them. Anyone else? Going once, going twice. All right. Thank you very much. Have a great afternoon. Stay safe. Thank you. Bye.